How's it going? Hope y'all are doing well today. Does anyone have any questions before we get started here? Okay. Alright, so today we're going to start Chapter 3. We're going to look at 3.1, maybe a little bit of 3.2. We'll see how that goes. And then from there, we'll just continue next week. I would anticipate our test being in 2 weeks over chapters 1, 2, and 3. So I figure between today and then Tuesday and Thursday next week, we should be able to finish all of chapter 3. And then we'll have the following Tuesday to review and then test on the following Thursday. Now, technically, we won't have a specific time for the test. It'll be set up as a Canvas quiz. And what I'll do is I'll give you a window from Tuesday night after we finish the review until the Monday night prior to the following week, or on the following week. So basically a 6-day period where you'll be able to take the test sometime during that window. So anyway, with that in mind, let's go ahead and get started on Chapter 3. Now, Chapter 3, here we're looking at numerically summarizing data. And so here we actually start looking at some of the different values that we use to describe quantitative data sets, and some of the different statistics that we calculate. Okay. Now, section 3.1 specifically is on measures of central tendency. So when we talk about central tendency, the idea is that we want to be able to find, where is the center of the set? And how do we define the center of the set? Because it turns out there's different ways. So as we go through and look at each of these different types of measures that we'll discuss, we'll talk about their pros and cons as far as, you know, whether, how organized a data set is, or how unusual it is, and how that affects what these values actually are when we calculate them. And we'll also introduce how to use our calculator to find some of these values specifically, although this will be more significant in section 2. So first, so when you talk about central tendency, the goal is to find a typical or we could also say average. We have to be careful about the word average in statistics, but average basically means a kind of a representative number. Now, we may think when we say average, we may think, what's the average age of students? Well, we can add all the ages together and divide by the number of students. Well, that's what we actually call the mean, and we're going to talk about that in a moment. Average does not necessarily mean the same thing as mean, and that's something that, when we're talking about statistics, we have to be very specific about. Average is more like this typical value that we're discussing. So there's actually 4 measures that we're interested in. There's the mean, there's the median, there's the mode, and we also have what's called the mid-range. So we'll discuss these 4 today in section 3.1, and then in section 3.2 we'll talk about measures of dispersion, I think is what we call it in this book, but basically how spread out or compact is the data set. Is it all kind of clustered together, or is it all spread out? So first of all, we establish where the center is in a data set, and then the second section we talk about how clustered around that center is the data. Okay, and that's kind of the idea that we're going for in these first 2 sections. Now, the other thing that we're going to look at is some of the notation that we use, and again, like I said, how to utilize the calculator to do a lot of this work for us, which is great. Okay, so we start with the mean. And the mean is typically described as the sum of the data values divided by the size of the sample or population, whichever one we're looking at. Okay, now depending on if we're looking at a sample or a population, we have different notation that we use for the mean. So if we say sample mean, then we mean, we'll represent this as x bar. And if we refer to the population mean, then we'll use the Greek character mu. Greek could be capitalized here, sorry. We use the Greek character mu to represent the population mean. It's important that we learn the difference between these two, because later on in other chapters we're going to have equations or formulas that have both of these values present. And so we have to know the difference between when we're working with a sample mean x bar and then a population mean mu. Okay. And for mu, what I like to do is just like to draw a U and then just put this longer leg piece on the front of it. So if you want some help drawing that. Okay. All right. Now, the other notation I want to introduce here is the capital sigma, which means sum of whatever follows. And again, that's Greek. And I stress that that's the capital sigma because we'll also be using lowercase sigma for something else in section 2. Okay, so that's some of our basic notation. So based on that, we can define x bar as the sum of data values x divided by sample size n, and we can define mu as the sum of data values x divided by population size n. Okay. So now we're working with the sample mean. We add up their data values, which data values we generally represent by x. So sigma x means the sum of all the data values, and then divided by the size of the sample if we're working with a sample, or the sum of all the data values divided by the size of the population if we're working with population. Okay. So again, whether we're working with a sample or a population is always relevant as far as how we do specific calculations and formulas, and as well as our notation. That's probably the most significant impact, is our notation right there. And it's important that we get our notation right, just to be able to accurately convey what we're doing to anyone that is following along with that, whether it's a person grading your tests or if you're actually doing research that involves statistics for any other class or job. So anyway, so that's some of our notation there. And that's the mean, and that's one of our measures of central tendency. We also have the median. Now, median, unlike the mean, doesn't have a lot of fancy notation attached to it. So for the median, this is just the middle value of a data set. And it's implied that the data set is arranged in order from low to high. So the middle value is the middle numerical value. That's what we're talking about. I might add that in. Okay. Now, for the median, there is one other thing. We talk about it being the middle value. If the middle falls between two values, then we'll just find the halfway point between those two numbers. Okay. And mainly that depends on whether we have an odd number of data values or an even number of data values. For an odd number, the middle value will be one of our data values, but if we have an even number, then the middle will fall between two data values. That's just the way it is. Alright. The mean, not the mean, the mode. I already talked about the mean, sorry. I knew what I wanted was 4 letters and I said the wrong thing. The mode is the data value that occurs most frequently. And this can be shared by multiple values. So it may be that our dataset has more than one mode. Okay, so we can have more than one mode in a dataset if they have the same frequency. That's the main thing. So we could have a dataset that's bimodal if it has 2 modes. It could be multimodal if it has more than that, but if no data value has higher frequency than anything else, basically they all have the same frequency, in that case we say that there's no mode rather than all of them being modes. So if all data values have the same frequency, then there is simply no mode. Okay. So that's our mode, and the last one we'll look at is the mid-range. Now the mid-range tends to not be as useful, but it's one that we go ahead and calculate. This is the data value that's halfway between the minimum and the maximum values. Okay, and so our formula for the mid-range is min plus max divided by 2. So if we want the value halfway between, that means we add them together and divide by 2. Okay, so that's our 4 measures of central tendency. Now, As far as when, as far as the effectiveness of these, as far as how they determine the measure of central tendency, a lot of the times we trust the mean and the median most of all. The median is nice when our data set is skewed. Whether it's skewed left or right, the median is pretty informative as far as roughly where the center of the set is. Mean is a little bit more reliable when we have a relatively symmetric data set as far as the values go. Now, if our values are pretty chaotic, then they're kind of all over the place, and there's not really any rhyme or reason to the values that we're getting. In that case, the mode might be more helpful for determining the center. The mode especially is most helpful whenever we're looking at qualitative data specifically, because we can't do any of the other calculations with qualitative data. Like, we can't find the average zip code of where everyone lives. That's not going to be anything we can reliably calculate. But we can find the most common zip code where people are living, and that would be our mode. Okay. Mid-range is not always useful either. It's one that we go ahead and calculate, at least because we can see kind of the cutoff between the bottom half of the data and the top half of the data, and how far the other central tendency values are from that. And there may not be any connection at all. The problem is a problem that we frequently run into in calculating these values is that a set may have what's called outliers. So an outlier this is a data value that is considered unusual compared to the rest of the data values in the set. That is so let's say it's a data value that's excessively large or small compared to the other data values in the set. Okay. So if we're in a class and most people in the class are between like 5'4" and maybe 6 feet tall, and then we have that one person in class that's 6'8". Maybe they play basketball. I don't know. That would be considered an outlier in that scenario. One person who is excessively taller or shorter than everyone else. The same goes with age. If we have one student most of our students are traditional, and we have one student that's non-traditional, then they would be considered an outlier in that class. If they're quite a bit older than the rest of the students. It's usually not just one person, that's the thing. But it's possible to have more than one outlier, but the smaller the data set, the less likely it is that we have an outlier. So to have multiple outliers, we have to have a pretty large data set for that to happen. So, and they'd have to be very different from the other data values. That'd be like in a class where most of the students make between a 70 and a 90 on the test, and we have one student that made a 20. A 20 would probably be considered an outlier. I hope no one makes a 20 on a test. Anyway, but if most of the class makes a 70 to a 90 on a test, and then one person makes a 95, It's really not that much further out, so it probably would not be considered an outlier in that scenario. Okay. Now, the reason we're concerned about outliers is that if there are outliers present in a data set, then it could certainly impact some of these different statistics that we're calculating. The median is generally regarded as being immune to the presence of outliers because there's not going to ever be too many relative to the size of the data set, so the median will still pretty accurately determine the center, especially if data is skewed to one side or another. The mid-range, though, is extremely vulnerable to the presence of outliers because the mid-range depends on the maximum and minimum values, and that's generally where the outliers will be, either the maximum or the minimum value. So, because of that, the mid-range is extremely susceptible to giving us data that doesn't really line up with the rest of the data that we have as far as statistics go. The mean is somewhat susceptible to outliers, although it is a combination of all the data values in a set, so a lot of the times that risk is mitigated. At the same time, it cannot be overlooked, because if we just have a small sample size and we have one number that's an extreme outlier, then it could have absolutely have an impact on the calculation of the mean and its effect, its value compared to the rest of the data. So anyway, so let's move on. I want us to look at a data set, and I'll just look at a relatively simple one. And I don't have any context for this data set. It's just a series of numbers that I like to use. Let's go ahead and include one more. All right. First thing we want to do is find the mean, and let's say this is a sample of numbers, which it is. If we find the mean, are we going to use x bar or mu to represent that mean for this data? Now, if you recall, if we're talking about a sample mean, we use x bar. Then if we're talking about a population mean, then we'll use mu. So what we'll be using in this case? Because we said we're talking about a sample, that tells us that it'll be x bar. They'll be representing the mean in this case. Now, to find that mean, we're going to take each of these 9 data values and add them together. So we'll take 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13 plus 21 and plus 34. Add those together and divide by 9. And let's see. So that's 4, 7, 12, 20, 33, 54, 89 divided by 9. So it looks like a little bit less than 10, but completing that calculation, we get 9.8, and this repeating. So I'm going to go ahead and, well, in this case, because we're working with whole numbers, we probably should round to the nearest tenth. So it might be better to say 9.9 in this case. It's 8 repeating, but whenever we round, the general rule that we like to use for rounding is we go one place beyond where our numbers exist. Like our numbers here are whole numbers. So when we talk about the mean, we'll go to one decimal place beyond that, which is the first decimal place. Okay, so for whole numbers, we round to the nearest tenth. If we're looking at money amounts, which are to 2 decimal places, to the nearest penny, then we would round our mean calculations to the 3rd decimal place, one place further. So we always go one place further in our approximations than the data is given as. Okay. So for any calculations we do with these, we'll just go to one decimal place. Is it 88, not 89? Four, 7, 12, 20, 33, 54. You're right. You're right, 88. Okay. Accuracy is also important, it turns out. Yeah, so this actually, that'll be 9.8 then, rather than 9.9. Okay, so that would be our sample mean, 9.8 x bar. Okay. Next, we want the median. Now the median, we said, was the middle data value. So which of the, and we have 9 data values here, like we said, so which of these would be in the middle? Five? Yeah, if we start counting from the outside and work in, we have 1 and 34, 1 and 21, 2 and 13, 3 and 8, and then 5 right in the middle. So we'll use 5 as our median. What about our mode? Mode, remember, is the term that occurs most frequently. 1, good. And the last one that we talked about is our mid-range. Now, we actually had a formula for mid-range, which is maximum plus the minimum value divided by 2. What is going to be the value of the mid-range in this case? $17.5, right? Because we take our maximum, 34, plus our minimum, 1, and and then divide that by 2. So that's going to give us 35 divided by 2, which is 17.5. Now, we look at all these values that we found for the measures of central tendency. We found the mean was 9.8, the median was 5, the mode was 1, and the mid-range was 17.5. All of them are very different values, so which would be the best way to look at this? Well, I'm going to show you, this is another type of graph. I'm going to draw a number line here, and I want to be able to get as high as 34, so start at 0, 5, 10, 15, 20, 25, 30, and 35. Now, we actually have two values at 1. I should finish making my marks here, sorry. And so our data values are at 1, and we have 2 of those. Then we have 2, and we have 3, and 5, we have 8, 13, 21, and 34. Okay. And so our mean says the middle of the data set is right here. So there's X bar. Our median is here. Our mid-range is over here. And finally, our mode, of course, was at the very beginning. Which of those looks like a better representation of what we would think of as the center of this data set? Now this is a little bit of a judgment call. Now eventually we're going to look at a way of determining, how, specifically how this is true. Does anyone have any opinion on which value better represents the center of this data set? So if we look at where our dots are located, most of our dots are over here, and we have a few that are getting further and further away as we go to the right. Now, I think we can safely rule out the mid-range as a measure of central tendency because it's nowhere near where most of the data values are. Most of the data values are in this clump over here. Mid-range is way over here, so it's not reliable in this case. In fact, it may be that 34 is considered an outlier. We actually have a way of specifically being able to calculate that. That's actually section 3.4 will go over that. 3.3 or 3.4, I don't remember exactly. But anyway, I think it's 3.4. So that may or may not be an outlier, but it's actually pretty far away from the rest of the data regardless. I think we can also rule out mode because it's on the opposite end of the numbers, just on the beginning. Even though there's two of them that have a value of 1, it's not really a center from how we think about it. Just visually looking at this, where the middle is, doesn't seem too reliable to call that a center, nor that. So probably it comes down to the median or the mean. I would say in this case the median is probably better because the data seems to be centralized here, with other values kind of going off to the right beyond that. Now, when we were talking about shapes of distributions in the last section, what kind of shape would you think this distribution would have? Is it symmetric, skewed left, or skewed right? Now remember, symmetric means it's, most of our points are congregated in the middle, and it kind of tails off to both the left and the right side. That doesn't seem to be the case here. Most of our points are congregated on one side, and it tails off to the other side. Now, the way that we defined skewed was whichever side had the tail, like the extra data values trailing off one direction, that would be the direction that we would refer to as being skewed. So in this case, most of our data is here, and we have a tail going off to the right. I would say this is skewed right in this case. Because we can see these values are getting further and further away on the right hand side, whereas they're pretty close together on the left hand side. And in fact, that agrees with something else I had said before, and that is if the data set is skewed to one direction or another, then the median tends to be the best measure of central tendency. Okay. And it's okay if you don't know that yet, but we need to be able to think about that eventually. And it's hard to look at this and try to imagine a bar graph, but we're just looking at where the values are centralized. And it's effectively telling us the same thing that a bar graph would. We have all these values over here, and then fewer values over here. So, yeah. Does anyone happen to recognize this series of numbers? There's actually a distinct pattern happening here. I just like to use this series of numbers because it allows me to find each of these things relatively easy, and it gives me a nice pattern to work with. Fibonacci, right. And the idea of the Fibonacci, I guess it's sequence, not series, because we're not adding all the numbers together. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on. And so each number in the sequence is the sum of the previous two numbers. And that's what the Fibonacci sequence is. So I like to use it for this example because it gives me a good list of numbers that have some interesting properties that we can illustrate and talk about here. It is in fact skewed right. Now it turns out I don't think 34 is actually an outlier, but it is further away than everything else, so it does have an impact on specifically the mid-range, but also the mean in that regard too. Okay. It is possible to have more than one outlier. It just depends on the number of data values we have. If we only have, like we have 9 data values here, it's unlikely we'll have more than one outlier. They would have to be very far away from the rest of the data for that to happen. But if we have like 50 data values, it is possible to have 2 outliers there. Yes. It just depends on how many data values we have and how far apart the data values are. Specifically the ones that we think might be outliers, how far apart they are from the rest of the data. As I said, there's a specific algorithm that we use for determining what an outlier is, so it's not really something we have to guess about. I mean, we can suspect something is an outlier, and then we'll be able to, after section 4, actually be able to calculate what an outlier is, and that should help us out a bit. Okay. Okay. Now, for this data set, let's limit this a bit. Now we only have 8 data values, so our sample size is 8. What is our mean in this case? Well, we know we have 8 data values. What's the sum of these values? 54, good. So if we just take 54 divided by 8, that gives us 6.25. Or 75, I'm sorry. Yeah. Now again, I said we would prefer to round this to one decimal place rather than have it 2 places. So we can say it's 6.8. Again, because all of our data is whole numbers, we want to round to one decimal place. What about our median this time? Yeah, the median actually falls between the 3 and the 5. So our median would be here. So if it falls between the 3 and the 5, what would we call our median? 4? Mm-hmm. Yeah, so we would add those two numbers together and then divide by 2. So 3 plus 5 is 8 divided by 2, which gives us 4. Mm-hmm. Our mode is still 1 since we haven't really changed that part of the data set. What about the mid-range? Mid-range is 11. Good. Mm-hmm. Yeah, and again, that's 1 plus 21 divided by 2. We're taking the minimum value and the maximum value and adding them together and dividing by 2, and that comes out to be 11. Now, once again, we see in the mid-range is not really a great representation of the what we would think of the central data value in this set, because 11 actually falls all the way over here, closer to the last 2 values than it is to the first 6, and because it's so far out of the way, it's really not a great measure of the center. The mean is actually a lot closer to the median now because we eliminated the highest term in the data set previously. But I would still say this is a skewed data set, so the median's probably the best measure for central tendency here. Okay. Usually whether it's a sample or a population, this will be literally included in the question. Like, it'll say if we have a sample or population, okay? And that's, the problem will start out in a sample of 25 adults, blah, blah, blah. Or in a population of, 3,000 students at a college, what is the average, whatever, okay? So we would certainly be able to discern from the problem, because most of the time it will quite literally be telling us that it is a sample. In fact, I would say just assume it's a sample unless they specifically say it's a population, because by and large it's difficult to work, or difficult to actually find in all the population data, much less work with it. Most of the time we are working with samples by and large. That's why the course is called statistics and not parameters, basically. So. Yeah, usually it'd be directly told. Occasionally we have to get context clues. Like if they tell us they survey 100 American adults, we know there's more than 100 adults in America, so we can assume that 100 people is a sample of American adults, not all 100 adults in America. So. Yep. It's another day with good sleeping in weather, so. I understand if you didn't quite make it on time, Gabriel. That's fine. I would love to be sleeping in this morning, personally. It's harder for me on Wednesdays because I have my 8 o'clock calls. All right. I want to go back to, and this is the data set that we had used in last class, which is this ages of students in an evening stats class. And let's see, I'm going to write these down again. We can consider this a sample. Well, that's a good question. Why do we not consider it a population? And in a way, we could consider a population. It's the entire population of one statistics class, or it could be considered a sample of statistics students from all statistics classes, or it could be considered a sample of students from a college. Okay. Since we're not specifically told that this is a population, even though it is all the students in one class, if we're talking about just this class, we could call it a population. But if we think of this as a sample of a larger number of students, I mean, if this is a portion of a larger number of students, that would be a sample. in this case, we could probably go either way with it. Fortunately, it doesn't really affect how we calculate anything. The only thing it affects is how we label things. But like I said, unless we specifically say it's a population, probably go ahead and use sample. That's a good guideline to go by. Now this one's a little bit more complicated because we're working with 20 data values, and unlike our previous data set, is by no means in order. Now, one of the things that the calculator does for us, and I would love to show you on the graphing calculator, but I actually need to go on by batteries because it's really just not doing a whole lot for me right now. Well, I could probably, it might hold together long enough for me to demonstrate this one problem. But all right, let me get out of that. If this calculator goes off in the middle of this example, I apologize. But it is on low battery, so. On the graphing calculators, the way that we can enter a list of data, and I'll have a handout for everyone. I'll make sure I post it to Canvas after class, so that will be available. We have our stat button here. Okay. Yeah, that one's that was all the juice it had. Sorry. All right. We'll look at this calculator instead. And hopefully by next class I'll have batteries for the other one. Alright. So in this calculator, the 36X, we press data, and you can see I've got some data in here already. Oops. Not a whole lot apparently. I'm just going to go through and delete everything. There we go. We actually have 3 different columns here where we can store data. The larger graphic calculators have 6, but we won't need more than 2 or 3 anyway. What I'm going to do, and again, the way that I got here is I hit the data button and it went right to this. And so we're going to enter our data, and I'm just going to do it by column: 18, 21, 37, and 18, 20, 18, 18, 32, 19, 25, 21, 45, 23, 20, 27, 19, and then 19, 29, 20, and 18. Now you'll notice right here it says we're on item 21 on this list. We know there's 20 data values here from when we worked with them before, but that's because this is the 20th one right here, and our 21st one was empty. So yeah, so we have 20 values entered in, and it doesn't hurt to go back through and make sure we didn't double hit any numbers. So like we have 3-digit number where we should have only 2-digit numbers, or if we didn't press a button hard enough and instead of writing 18 maybe we just wrote 1, and that would throw off our results as well. But it looks like these are all good. So we enter all the values here. All we did was type in the number and press enter. Okay, so next we want to calculate our statistics for these numbers. Now that would be right above our data button. It says stat and reg/distribution. So we'll press that button. We want one variable stats, which is option 2. Our data is in list 1, and for frequency we just use 1 because we hadn't entered all the raw data individually, so we don't worry about frequency in this scenario. And then we go to calculate. Now it's going to give us a lot of different things that we haven't talked about yet. First of all, it gives us X bar, which is 23.35. So that would be the average age of students in this class. Okay. Good, good. S, we haven't talked about that, but this is standard deviation. That's in section 3.2. Sigma is the same thing. Sum of X, that's the sum of the data values, 467. We don't really need that. It already calculated it for us. Tells us the minimum is 18. Q1 is the first quartile. We'll talk about that in section 3. And then the median is 20. Good. Q3, that's the third quartile or 75th percentile. We'll again talk about the quartiles and percentiles in section 3. And then our maximum is 45. Now, so you'll notice that we found the median and the mean. We can use the max and the min values to calculate the mid-range. And it does not give us the mode. That's the only drawback. But the mode is, we said 18. Good. And the mid-range, because we know the minimum and the maximum values are 18 and 45, we add those together, divide by 2, so 31.5. Good. Okay. So we can certainly utilize the calculator to make this an easier process. As far as, especially when we have this much data, 20 is not bad in the general scheme of things, but when we work on the project this semester, we're going to have 50 data, 50 things of data. We'll definitely want to use some kind of technology, whether it's the calculator or if you're adept at Excel. Definitely want to use one or the other to be able to find those means and medians, especially because that's going to be a difficult calculation otherwise. Any questions on that? Now we're going to do a lot more of that with the calculator, but like I said, I'll be sure to upload an instruction sheet for using both types of calculator, the 36 that I showed you, as well as the 83s and the 84s, which are essentially the same for the most part. Okay. So the calculations that we did there, that's useful for everything that we do in this particular chapter, because notice that we found a lot of the things that we're going to talk about for in section 3.2 and 3.3, which are the standard deviation and then the quartiles or percentiles. So we'll be talking about those in the next couple of sections beyond this one. And so that's kind of just an introduction to the calculator. And I encourage you to try to do that on your own calculator. Like I said, it's a little bit different on the 83s and 84s. And like I said, I'll have some batteries for next time. That way I can demonstrate on the 83 that I have. Alright. So let me look at the homework that we have. So on page 127, I want you to look at 21 and 27. And for those problems, rather than following the instructions that they give, just find the four measures of central tendency. And you can use any method that you like, whether you want to do it by hand or by using the calculator. I do encourage you to try to figure it out in the calculator, because I think it'll make it much easier for us as we continue from this point, being able to use the calculator. And you'll be able to use it on the test for sure. That's partially why I want to encourage you to get started now. It's just getting accustomed to it. But yeah, you can do those either way for now, just starting out. So it also talks about finding whether creating a histogram and determining whether the data is skewed left or right, or if it's symmetric. If you want to, for those two problems, you could do like a number line plot like I showed you before, and kind of use that to figure that out if you like. But at least want you to do this much. Okay. There's actually another metric I'll show you. I don't really want to worry about it today. That allows us to compare the median and the mean and determine if the data is skewed left or right, or if it's symmetric. And so we'll talk about that starting next time. Alright, so that's all we have for today. Hope everyone has a good rest of the week and weekend, and I will talk to you again on Tuesday. Have a good one.